In this video, we're going to link the thermodynamic equilibrium constant to Gibbs free energy, or what's now better known as just free energy. So the equilibrium constant that we studied in chapters 14, 15, and 17, K, expressed in partial pressures and molarities, can be calculated using the following equation. So the non-standard, so the not meaning standard, the non-standard is the Gibbs free energy, standard free energy at 25 degrees Celsius and 1 atmosphere is RT times the natural log of Q, where Q is the reactant quotient. At equilibrium, this rearranges to be that the standard free energy, or Gibbs free energy, is equal to negative RT natural log of K, where R is the gas constant of 8.31, because we use this value when we have energy, which gives us in kilojoules, and it's in joules per mole K. Temperature, therefore, has to be in Kelvin, and K, of course, is the equilibrium constant. So, some problems here. So I've given you the balanced equation, the equilibrium, and then I've given you the Gibbs free energy. So first thing we have to do is calculate what the standard Gibbs energy is. And so for this equation, delta G naught is going to be the delta G of formation for CaO plus the delta G of formation for carbon dioxide minus the delta G of formation for calcium carbonate. Okay, so I've given you those values already, as I will do on the test. So this is going to be a negative 603.5 plus a negative 394.4 minus a negative 1128.8. So the first numerator becomes negative 997.9. This becomes plus, because of negative and negative, 1128.8. So my delta G naught is 130.9 kilojoules. Now, because R is 8.31, but most importantly, it's in joules per mole K, I need to change this to joules. So delta G naught is 130,900. Get rid of the comma because it confuses people. Joules. And then I use the equation that delta G naught is a negative RT natural log of K. So I have 130,900 is equal to negative 8.31 times the temperature is going to be at 25 degrees for all of these, so 298. So even if it's not given to you in the delta G naught, this means 25 degrees C, natural log of K. So I have 130,900 is equal to a negative 2,476.4 natural log of K. So I'm going to divide both sides by that negative. So I have 130,900 divided by a negative 2,476.4 is equal to natural log of K. This negative 2,476.4 is going to be constant because R is constant and T is going to be constant for these. But your delta G is not going to be constant. So I get natural log of K is going to be a negative 52.85, and K then is e to the negative 52.85. So K ends up being 1.10 times 10 to the minus 23. Okay, so positive delta G is non-spontaneous. Very low or small K is mostly reactants, which means it also did not go forward. Okay, so those two things should correspond to each other. All right, let's do another example. okay, of the equilibrium constant when I decompose dinitrogen tetraoxide to 2 nitrogen dioxides. I again have to calculate the delta G naught, so delta G naught is going to be 2 times the delta G of formation of NO2 minus the delta G of formation for N2O4. So delta G naught is going to be 2 times 51.3 minus 97.82. So delta G naught is going to be 102.6 minus 97.82. So delta G naught is equal to 4.78 kilojoules, and delta G naught is 4,780 joules. Okay, this means near equilibrium because it's less than 10. Okay, and so then I also have the fact that delta G naught is negative RT natural log of K. So I have 4,780 is equal to negative 8.31 times the 298 natural log of K. Like I said, this is basically going to be the same every time. 4,780 is equal to a negative 2,476.4 natural log of K. So 4,780 divided by a negative 2476.4 is equal to natural log of K. So natural log of K is equal to a negative 1.93. K then is e to negative 1.93, the opposite of natural log on both sides. So K becomes 0.145 near equilibrium, or I'm going to say at equilibrium. Referring back to chapter 14. Okay, and the last example, I suggest trying this one on your own before I do it, and then coming back to see if you got the right answer. Same process we just did. Delta G naught is going to be equal to the delta G of formation for magnesium 2 plus 2 times the delta G of formation for OH minus the delta G of formation for magnesium hydroxide as a solid. So delta G naught is going to be a negative 456.0 plus 2 times a negative 157, it's a very bad 7.3 minus a negative 933.9. So delta G naught is going to be a negative 770.6 plus 933.9. So delta G naught ends up being 163.3 kilojoules. Again, has to be in joules, so 163,300 joules. And then delta G naught is a negative RT natural log of K. So I have 163,300 is equal to negative 8.31 times 298 natural log of K. So I have 163,300 is equal to a negative 2,476.4 natural log of K. So 163,300 divided by the negative 2,476.4 is equal to the natural log of K. So the natural log of K is equal to a negative 65.94. K then is E, the opposite of natural log, of negative 65.94. So K ends up being 2.30 times 10 to the negative 29. Okay, and again, a very small equilibrium constant means it's mostly reactants. This negative 29 means that it's mostly reactants here. And a positive delta G also means it's non-spontaneous, so those two things agree. And that is the end of this video.